training and instruction on principles of steam sterilization, and we've published some articles, and we'll do some in-person presentations. But back in February, we started a webinar format with the hopes of being able to present to more people. So we hope this is of benefit to you. There are more complex issues that can arise as you're trying to, say, validate a complex load, or and we may not cover some of those more complex things. For this reason, we do encourage you to use the feedback questions feature to ask us any questions pertaining to any topic that you would like to ask. Like Amanda said, unfortunately, due to time constraints and the number of attendees, it's difficult to cover everything. But what we've been doing is if you do submit those questions, usually within a week or maybe even a couple of days, I'm able to field those questions, do any research that might be necessary if it's something that I haven't encountered before, and then get back to you. What I hope to do this time around is provide a frequently asked questions, kind of a question and answer thing where I can sum up some of the questions and make available to all. And of course, the broadcast, I believe, is set out. If you had questions about that, please email us, and we'll try to help you. So today, as Amanda mentioned in the introduction, we're going to talk about principles of steam sterilization. And these 4 bullet points that you see on the screen: 1, factors that affect steam sterilization. We're going to look at 6 principles, as a matter of fact. And then typical cycles, how the cycles then are addressing those 6 principles and how they all play together. Adam is going to talk with us a bit about measuring performance. This is kind of a new added feature to this presentation. I used to present a couple of slides on this, but it isn't really my area of expertise, so I'm glad that Adam's here with us today to go through this in a little bit more detail. And then, of course, we'll talk about some common challenges. So moving on, here are the 6 principles of steam sterilization that we want to spend some time addressing today, because really failure to achieve sterilization typically arises from an issue with one of several principles of steam sterilization, those being time, temperature, steam contact, air removal, steam quality, and drying. So we're just going to go through each of these principles one by one and discuss them briefly. And of course, if you had any questions, put those down and we'll be sure to get back to you. Time. We want to start off talking about time because it is a crucial component of sterilization. You may ask, why is it a crucial component of steam sterilization? And the fact of the matter is that not all organisms die at the same time. As a matter of fact, if you look at the chart there, you can see a linear graph where we have on one axis, the y-axis, the log number of survivors, 6, which equates to 1 million spores, and then you have along the x-axis the exposure time in minutes, so the time it takes to go from 1 million spores down to 0. And how we usually speak about these things is in terms of a log reduction. So 1 log reduction would be a reduction in the microbial population of 90%. And as you can see then, the amount of time that it takes to reduce that population by 10%, we call it a D-value. So in this particular graph, the time that it takes to go from 1 million spores, and I should add that these are Geobacillus theraphomophilus spores because that's an industry standard due to their resistance to moist heat sterilization. But the time to reduce at 1 log is 2 minutes. So if you start with 1 million spores, it takes roughly 12 minutes to get down to 0. And of course, you can go beyond that to say if you were to set your sterilization cycle for 20 minutes, you would reach 10 to the negative 4th. This is a principle called overkill, which is an acceptable principle in the industry. Now you also see on the chart that right there in the corner, 121 degrees Celsius, because there's a correlation between the time and the temperature, so that if you increase the temperature, you can decrease the time. So the second critical factor, alongside with the time, is the temperature of the saturated steam. Right in the middle of this chart, you can see 250 degrees Fahrenheit or 121 degrees C, and there's the 12 minutes that we referenced on that log reduction chart that it took us to get down to 0, and it took 12 minutes. You can go up and down this chart. If you were to increase the temperature by 20 degrees Fahrenheit up to 132 C, it'll take 0.9 minutes to achieve the same results. And then you can kick it up to 140 degrees C, and it'll take you 0.13 minutes to achieve the same result. So obviously, the temperature has a significant impact on the time required to sterilize. And of course, conversely, as you decrease the temperature, you can see the length of time increases dramatically. 12 minutes is kind of a standard at 121 that most labs or pharmaceutical companies use. You can use higher temperatures. We see that more often in hospital settings, where they'll use 4-minute cycles at 132 or 140. Primarily, the differentiator is that in hospitals you're sterilizing a lot of stainless steel. In many lab environments, if you subjected some of glassware or cages or our typical things that we're sterilizing at higher temperatures, they tend to degrade. So 121 for 20 minutes is kind of a standard sterilization cycle. Beyond the time and temperature, the next important thing is once you have those established, that's good. But what we need is for that steam to make contact with the load. The amount of energy stored in steam is much higher than dry air or even water at the same temperature. But that energy, which is much higher, about 7 to 8, I think it takes about 7 times the amount of energy to keep steam as it requires to make steam, turn water into steam. So it's a significant amount of energy in that steam, but it has to be released. And it's only released when it condenses or when it contacts the load. Thus, for sterilization to occur, steam must make contact with the load for it to be effective. My daughter had that experience this morning after she popped her microwave into the microwave for water and oatmeal, took it out thinking that she was just grabbing the cooler part of the bowl, which indeed she did, but she had her hand awkwardly over the top of the bowl and quickly dropped it on, thank heavens, under the counter because that she felt that steam contact. And most of us have had that experience, so we can begin to understand how that steam releases its energy. And it is different than, say, just sticking your hand into an oven at 250 degrees. It's not comfortable, but you could certainly put your hand in there and wave it around and not have the same experience that you would when that steam actually condenses on your skin. So all that to say that once we have our correct time parameter and temperature, so whether it's 121 at 20 minutes or 140 for 4 minutes, that's good, but the steam still has to contact the load. And what we find, however, is the biggest deterrent of sterilization is air, because air will be the biggest deterrent of allowing steam to contact the load, because it's so much denser than the steam. It has great difficulty penetrating the air to contact the load anywhere that air might be trapped. So you can see in the very primitive diagram I have there, the steam trapped above the air. But what we want to do is get the air out of the chamber, out of the load, all the cavities that are within the load. We need to get the air out of there to allow the steam to penetrate. And in a typical autoclave, we'll do that through one of two means. The first way would be what we call gravity displacement. We're just going to basically pump in steam and push the air down the drain. That would be just in a pure gravity sort of cycle. You can You can do better than that if you utilize a vacuum, in which case air is removed from the chamber mechanically via a water injector vacuum system or a vacuum pump, where you're going to pull a vacuum, and you'll have much greater success removing air, especially from porous items or anything that will be prone to trap air. And we'll actually look into some of the details as to what we would put in a vacuum versus a gravity cycle in a few minutes. But suffice it to say for now that with air being the biggest deterrent of sterilization and prohibiting steam contact, even if we have the ideal time and temperature set up, we need to get the air out of the chamber. And of course, look for areas as we're thinking about our load where we might be trapping air. Now, up to this point, these first four that we've talked about, time and temperature, steam contact, and air removal, we have some control over, either through the way we set the sterilization cycle parameters of time and temperature. Usually those are configurable on your machine. And of course, we have some control as we look at our load and analyze it for making sure it's not too dense, not too overpacked, that we don't have glassware that is sitting upright and creating an air pocket to trap air for just, say, using a gravity cycle. Something that's maybe not so much in our control, but we do want to at least give mention to, is the steam saturation, the amount of moisture in the steam. Steam contains the greatest amount of moisture when there's no liquid condensate present. We want to have as much steam packed in there in the form of steam, not water, as we can. And of course, when it comes to this, it's a difficult problem for any of us to address, and usually would require the help of your facilities personnel, or possibly a manufacturer or a service organization. They can come in and test the quality of your steam. But we want to do that and understand that, because we could have two potential problems. They're relatively rare. Don't see them a whole lot, but they can be problems. And of course, the first would be, on one side of the scale, would be wet steam. The problem with wet steam is it has a lot of water. And as we talked about, the amount of energy contained in steam is much higher than the energy contained in water. So what we lose with a wet steam is a diminished amount of energy. We will tend to make coverage. Things will be wet. You probably have a wet load when you're done. But what you're lacking there is a significant amount of energy simply from the water that is present. And of course, water has will further break down the steam as well, and that's going to decrease the efficiency of sterilization in the cycle. And if, on the opposite side of wet steam, probably be a superheated steam. So here, we've got the appropriate temperature we need, and we've got certainly an increased amount of energy, but the problem is we need the contact, and the contact comes from the moisture. So where you don't have the moisture available in the steam, you're also going to fail to sterilize adequately, or you're going to be not as effective in either of these situations, wet steam or dry steam. What we're looking for is in that around 97 to 100% saturated steam to be effective. And then finally, the last principle that we want to talk about is drying. This is at the end of the cycle, and it's important because, for proper sterilization, we don't want items to be wet when they come out. Liquids and open air are ideal transmitters of contaminants, so ensuring a load is dry is necessary to prevent recontamination. Now, drying is typically the last part of the sterilization cycle, and usually it occurs as a vacuum is drawn. Since when we draw a vacuum in the autoclave, or anytime you're under a vacuum, the boiling temperature of water decreases. So it takes less energy, less heat for that water to boil and evaporate. So we pull the vacuum, and then the amount of heat that is contained in the items being sterilized itself kind of provides that source of heat to basically dry itself. Now, if you have items that have low specific heat, like rubber stoppers or plastic, that's where, of course, you're going to run into challenges with drying. Glassware, stainless steel, items like that, they have higher specific heat and much more effective in essence drying themselves. So those are, up to this point, the 6 basic principles. We'll come back around. We'll be hitting these again as we look at the sterilization pipes and then some of the challenges. But let's take a minute. I want to talk about 3 basic sterilization types that we use in the industry. The first one is a gravity cycle. It's your basic sterilization cycle. A pure gravity cycle will incorporate no vacuum. You can incorporate vacuums into a gravity cycle and a purge, or maybe some drying time. But basically, you are putting steam into the chamber and pushing the air down the drain. And it is perfectly effective for sterilizing most things, but especially metal components, glassware, non-porous items that don't trap air. Gravity cycle is very sufficient. The pre-vacuum cycle then is used for porous goods, double-wrapped goods, tubing with a small lumen that simply forcing steam into the chamber is not necessarily going to penetrate through to the middle of the tube. We're going to want to remove the air from that tube. Glassware that cannot be, for whatever reason, you can't like lay it on its side or turn it upside down. It has to be standing up. Fermenter comes to mind, or tall, for whatever reason, it can't be laid on its side or turned upside down. That pre-vacuum cycle is going to be required to remove the air from inside. Otherwise, it's going to sit at the bottom of the container, not able to fall through the solid bottom of the container and out the drain. So we use a pre-vacuum cycle to ensure air removal in those sort of challenging loads. And then finally, the liquid cycle. A liquid cycle really is just a modified gravity cycle, and it should be used for liquids in vented or borosilicate glass. The difference between the gravity cycle and the liquid cycle is in the exhaust time. So we've brought the liquid to temperature, obviously well above boiling at 121. We've had an exposure time, and then when it comes time, of course, to exhaust the chamber and cool the load, we can't let up on the pressure that's in the steam sterilizer right away. We have to slowly let that out so that the liquid kind of comes down gradually while still being under pressure. So those are your 3 basic three basic sterilization cycles: the gravity, pre-vacuum, the liquid, by which we perform the sterilization. Let me briefly go through some of the phases where we accomplish the principles we've been talking about. There's usually a preconditioning phase. It might start with a purge. I think of a typical pre-vacuum cycle where we will open the drain and both pull a vacuum and push in steam, and maybe a minute or two, all that to begin to remove the air. And part of that air removal, but it's air removal. So if it's a gravity cycle, we're pushing it out with steam. If it's a pre-vacuum cycle, we're going to run pulses up and down to pull a vacuum and pressurize, and pull a vacuum and pressurize. All that is pushing air out. Once we reach, after it's performed those aspects, then it begins to raise the temperature to the sterilization temperature, or what we call the exposure phase. So we preconditioned, we got rid of the air, we brought the temperature and pressure conditions in the chamber up to what we're looking for sterilization, 121 or 140. Then we enter into the exposure phase. That's where the timer starts, whether you're doing 12 minutes or 45 minutes, whatever you happen to be doing. That exposure time will run based on time. Usually it's monitored by a RTD probe in the drain, and it's monitoring the temperature that's in the chamber, knowing that that's usually the coolest part of the chamber would be in the drain. So if it's hot, if they've got a good temperature there, your temperature in your chamber is good as well. So we start the time clock with the exposure phase, and of course once that's done, then we can move into post-conditioning, which is drying if you're talking about hard goods, or the slow liquid exhaust for a liquid cycle. I want to turn it over to Adam, because you can do all that and be very successful in making sure that your loads are packed right and that you programmed your autoclave with the correct time and temperature. But at some point, you really do want to step back and make sure that you are, that your autoclave cycles are performing to the way they need to. So Adam, why don't you take it from here?
Thanks, Ken. So as Ken mentioned, there are several ways to measure performance of your steam sterilization process. Two of the more common tools used to verify your cycle is the biological indicators, or BIs, and or chemical indicators and CIs. Really the idea here is to provide a level of assurance that the load has reached the parameters critical for a successful cycle, as Ken's been talking about. So what is sterility assurance? It's a way of evaluating or monitoring the sterilization of various products to ensure that all pathogens or disease-causing microbes have been removed or destroyed, and to provide protection from recontamination. BIs and CIs are used as a supplement to physical monitoring. Looking at the simple pyramid below, you can see the three levels of products that are used to indicate sterility assurance. As you move up the graph, you increase the quantifiable level of sterility assurance. So at the bottom are your normal CIs, which include your process indicators, then your chemical integrators, which include your class 5 and 6 CIs. And your class 5 and 6 integrators measure all critical parameters in steam sterilization. So you have your time, temperature, and presence of saturated steam. In addition, the class 5 integrator is designed to meet or exceed BI performance requirements. And then obviously at the top you have your BIs. So what are biological indicators? BIs are actually microorganisms, or spores in this case, that are placed on a substrate to prevent or present a worst case scenario for steam sterilization. Basically the working principle is that if you have a high population of a resistant organism to steam, that can be inactivated by the sterilization process, then there's a high probability that all other microorganisms at that location in the sterilizer will be inactivated as well. So BIs come in many different shapes and sizes. I've listed some of the more common formats on the slide. The most common substrate is a strip usually made out of filter paper. In a lot of cases, it's packaged in a glassine envelope. Another format is a disc. These are small round pieces of filter paper, which is used in areas that a normal strip cannot fit. When looking for the right option, though, for your process and facility, some things need to be considered. And these include, again, the space available to place the BI, any substrate requirements, the population or number of spores on each strip, the D value, as Ken talked about, or the resistance of each lot. And another important consideration should be the capabilities of your micro department. For instance, if you are able to process BIs aseptically. If you're not, then a self-contained biological indicator, or SCBI, may be your best option. SCBIs are, as the name refers, totally self-contained and do not require aseptic transfer of the BI into sterile approach media. The system is designed to eliminate the challenges and time needed for aseptic handling. So the design consists of a plastic vial and cap, paper disc inoculated with spores, crushable glass ampule containing culture media, and pH indicator. At the end of the cycle, simply seat the cap, crush the ampule, and incubate. Usually a chemical indicator is placed on the vial as well for quick recognition of a process FCVI. So what are chemical indicators? CIs are usually inks or dyes that are calibrated to measure certain criteria for steam. Again, talking about temperature, time, and saturated steam. In the presence of one or all of these parameters, the ink changes color, indicating a pass or fail cycle. So if you compare these to BI, CIs can give you an immediate indication of a failed cycle and do not require aseptic processing or incubation times. The different types of CIs are defined based on which parameters they measure. And if you look at ISO 11140-1, it defines the 6 classes of chemical indicators. And the indicators are subdivided within these 6 classes based upon the information they relay to the user. So class 1, those are your external process indicators that are used to distinguish between processed and unprocessed material. Class 2 are for or used to evaluate specific tests, and specifically they really do refer to the Bowie-Dick type test and air removal type test, which we'll discuss in a couple slides. The class 4 is your multivariable indicators. These will evaluate 2 of the 3 critical parameters of steam, and these usually include your control tubes. And then you have your class 5 and 6 CIs, which again measure all critical parameters. The difference between, and I get this question a lot, the difference between the class 5 and class 6 is really cycle specific, and BI correlation. So the class 6 CI, they're really designed to be cycle specific. So each cycle with different time or temperature, you would have a separate CI. With the class 5, it can be used at 121, 132, or 134C. In addition, their performance is required to correlate to a biological indicator. So as a result, the class 5 integrator results are similar to those of the BI and can detect failures where the selected temperature isn't reached. Just real quickly here with this, this graph just represents the different classes and the parameters used against the acceptance criteria. The last thing I want to point out in regards to the ISO classes is that the classification structure is used solely to denote the characteristics intended use for each type of indicator. So the classifications have no grading significance, meaning one class is not better than the other. They only relay different information to the user. The last topic I wanted to cover before handing it back over to Ken is air removal. Ken's done a great job of talking about why air removal is so important. Being able to detect air removal is crucial to ensuring a successful cycle, especially when you're talking about your pre-vac or vacuum cycles. So when using a pre-vacuum sterilizer to remove air, a Bowie-Dick type test should be used. These CIs utilize a steam-sensitive chemical indicator in porous barrier or challenge material, usually a paper in most cases, as you can see in the bottom image there. The test serves as a heat sink in otherwise empty chamber. So to test the sterilizer, you place one test pack in an empty chamber directly over the drain and run the pre-vac cycle. Once completed, you basically unwrap the indicator and view the color change. Any air not removed during the pre-vac cycle will be concentrated in the test pack, and residual air prevents steam contact with the chemical indicator, which obviously would prevent the color change. The very last point is that the air removal test really should be performed on a daily basis, and if you're following ISO, is recommended by ISO 17665-1. So Ken, take it back to you.
All right. We want to look at some common challenges and look at some mistakes that are made along the way that we've witnessed in the process of sterilization. I have some of these I have kind of categorized under the specific principle that it applies to. Some of them are just, some of these slides are just more specific to certain particular challenges. But we think about steam contact and what we need to watch out for practically when it comes to making sure that we don't have areas that are going to prohibit steam contact. Of course, would be closed valves, tightened screw caps, or secured aluminum foil. I know sometimes it's very common to cover glassware in aluminum foil. Be careful, you're rubber banding it not to do that so tight. Tied waste bags. You can see a picture there of a waste bag that was zip tied shut. I see that sometimes. This actually is one of my experiments that I was doing, so that was my intentional mistake. I've got a load probe in there trying to see just how effective it is to create, to reach temperature in the middle of the bag as situated like that. There's a little space for air to be removed, but not too much. So, and of course, the other thing is, as you look at your load, anywhere where area is enclosed very tightly or the load is packed very tightly, could be an area where steam is going to have a very difficult time contacting. So, of course, and sure valves are open. Inspect loads for spots that are kind of completely closed off. Don't pack loads too tight. The other thing about packed loads is it leads to an inefficiency. We want to be efficient, so we pack it tight. But at the same time, the denser the load, the more the steam's broken down and condenses, and of course, then the longer we have to continue to eject steam to bring things up to temperature. So you actually can lengthen your cycle in doing that as well. And of course, if you've got the decom bags, at least leave some air allowed to escape and for steam to penetrate. If you can use a gentle vacuum, that is very helpful within this scenario. But I understand if you're autoclaving like Petri dishes that were filled with auger, that can be problematic in a regular pre-vac cycle because they will boil over and you will have some flash evaporation and a mess to clean up in the autoclave when you're done. Insufficient air removal. This would be not just areas that are going to prohibit steam from contacting load, but areas that are going to trap the air in. Case in point being that the decom bag I showed would have done both. Prohibited steam from contacting it as well as not allowing air out. But anything that's very heavily wrapped goods, bottles or pans that are not inverted or placed on their side. If you're going to load up your glassware bottom down, remember that you want to choose a pre-vac cycle. Make sure you're hitting that button and not the gravity, because that air will get stuck on the bottom of the beaker or flask or whatever it happens to be, and have a very difficult time getting out. You can see one picture here. This was another challenging thing. Those were cages, actually, with bedding in them. They're put together and then wrapped and sealed, and they were being autoclaved on a gravity cycle. They were needed to be autoclaved a very, very, very long time to achieve sterilization, as you can imagine. And the cages started to break down over time, which is not surprising. So, solutions is ensure, again, empty bottles will hit outside or inverted, switch from gravity to vacuum cycles. In some of the more challenging loads, you may want to make sure that your vacuum pulses are reaching at least 28 inches of mercury or 94.8 kilopascals, depending on what measurements you're using. The pre-vacuum is very necessary for removing air, but also watching how you configure loads, checking your vacuum pulses and seeing, making sure you're pulling a significant vacuum if you're concerned that you may have air trapped. Water droplets and or stains found outside of wrappers. This can often happen. You notice some stains or droplets. Check your load. Sometimes we see as you're configuring your load, your denser items are, of course, going to be your cooler items. And so steam's going to condense on them much easier. And if they're on the top, which we see from time to time, they're going to be more prone to drift. So if you can rearrange your load so that your heavier, denser items are on the bottom, this will keep them from dripping down on the items below. And the other thing someone said, and I've never tried this, but you'll place the cotton sheet on the shelf prior. If you can't avoid that, if the whole load is dense, a cotton sheet to catch some of that may help. And it's going to still allow air to be pulled through the cotton, so you're not going to trap air in that way. Water droplets found inside of pouches. If you happen to use pouches, you do want to make sure that preferably they're lined up, as you can see in the picture, kind of on their side so that the steam can, so that any condensate inside the pouch, because there will be some. Otherwise, if there wasn't, we wouldn't have had steam contact hitting, in this case, the scissors or the forceps. You're going to have condensation, but you want the pouch to be arranged so that the steam can drain out. Certainly not with the clear side down, because the breathable side is the white side. So you at least want it down, if not on its side. Liquids placed in deep pans to catch boil over. We see this sometimes, and it's very tempting to do because nobody likes to clean up baked media off of an autoclave floor. However, we do need to understand that in some of these Nalgene containers that are like 5 inches high, you do risk trapping air in the bottom of that. That's a little high for gravity cycle or a liquid cycle for that air to be pushed out over the side. You will greatly increase the length of your sterilization time, or the time it's going to take rather to bring liquid up to temperature in that case. In a case like this, with the small test tubes, may not be so bad because you're talking about a small amount of water. But if you've got larger amounts of water, 500 milliliters or 1,000 milliliters a liter, it can take a significant amount of time to bring those up to temperature. In the first place, putting them inside of a container where you've got a kind of an air pocket of prohibiting steam from really circulating around the entire glassware will really increase the time. And of course, if you not happen to be using a probe, you're just setting your autoclave for a certain amount of time, you're making the assumption that you're actually bringing the liquid up to temperature in the time frame of your cycle, and you may not. You may be getting through your exposure time, and your liquid's only at 116 or 117 C. So try to remove the deep pan. Use a shallow 1-inch pan. Last time I did this, I got lots of requests about where to find these, and they're not easy to find. I checked with some old veterans, and they assured me that, hey, cookie trays will work just fine. If you something that's about 1 inch or less, the air will be able to be kind of pushed off of that and allow steam to really circulate nicely around glassware, and you'll have something underneath to catch any boil over. And then I was just alluding to this. Watch your liquid come up time. Understand that the amount of time required for liquids to come to temperature it can be significant. So you can approach it one of two ways. One is use a load probe. You can see a load probe stuck into this. It looks like they were missing the cap with the hole in it. But just to kind of test and make sure your water is coming up, or your liquid is coming up to temperature. Most manufacturers, I believe, probably provide some of a chart that might say, hey, if you're autoclaving 1,000 a liter of liquid, utilize maybe 45 minutes, and what is factored in there is not only adequate sterilization time, but also includes the amount of time it would take to come up to temperature. So you don't short circuit your liquid cycles. Remember to give them adequate time to come up to temperature. And then watch the way you pack bottles. Bottles packed together tightly will increase the time required for sterilization. It's often recommended if you're going to pack them close together. Say you've got, it might take 20, 30-minute cycle exposure time to do 200-300 milliliters of water. But if you pack it all together, you want to kind of treat that as one big amount of water. So 1,200, 1,500 milliliters of water if they're all packed together with minimal space, a lot for the steam to get in and out. So provide space around each bottle, lengthen exposure times if necessary, use load probes and F sub-zero calculations. We didn't talk a lot about that in this particular webinar, but the F sub-zero is a calculation that calculates the amount of kill that is happening in a load while it's coming up to temperature. Some people use it all the time, some people will not use it, but it's a legitimate calculation. A lot of them will start calculating amount of kill from about 110 C up to 121, and then that will shorten your time if you need to try to reduce your cycle times. So that's all we have today. If I didn't happen to touch on any of the issues you're experiencing, or if you have any questions, again, please submit those questions to us. We will make every effort to get back to you here in the next couple days. And so we really appreciate you being with us today. Thank you very much.
Thanks, Ken, and thanks, Adam. I'm going to keep this open for a little bit, maybe 5-10 minutes, and you guys can continue to put your questions in the questions panel on your GoToMeeting screen. I just wanted to thank you all for attending our webinar today. We appreciate you taking the time to learn with us and hope you found this session beneficial. And thanks again. This concludes today's webinar.